Okay, so the review sheet that is available on Moodle should cover everything. I did not intentionally leave something off of this that is covered on the test. Okay, I did not intentionally do that. However, I didn't sit there and go through the test with every little question and make sure that I had a corresponding bullet point on the sheet. Okay, so there are maybe an item or two that we haven't covered. I mean, the vocabulary is sort of broad, right? That's all vocabulary, right? Stress, strain, Courbet lattice, interstitial, all these different terms that we've learned. You've got to be able to know and define. I think we can almost get to fit on one sheet. So I think that should, yes, sir.
When you say know and define, you mean like you're really going to have a listing there and we're going to have to...
Short answer kind of definition.
Oh.
And I recommend that if it can be defined in, if you can make it easier by writing an equation, do it. I mean, most of the time you're going to have some kind of verbal description, right? So if I were defining Poisson's ratio, right? That was just, somebody was asking, was it Poisson's ratio question. So if I said Poisson's ratio, I could write nu equals minus e sub x over e sub z. But I really need to define, that means it's the ratio of strain in the lateral dimension to the strain in the tensile direction. Right? So I'd have to show that I know not only this is how you calculate it, but what ex and ez mean.
Okay, so what if you don't know the equation, but you know...
Well, that's fine. You can know the words, that's fine. But if you want it, you can simplify it by just writing the equation and then just saying where ex equals strain and lateral strain and ez equals longitudinal strain.
So how many questions are there?
There are, so all of the vocabulary is all sort of one question. And there are 7 questions.
How are you grading all 7?
I am grading all 7, 100%, everything. There are 100 points. Actually, I think there might be like 98 points on the test or something. In which case, I'll give you 2 points for putting your name on it. I don't know.
2%.
I have a question, which is, here's a bunch of terms, define them. Right? Because again, that's the nature of material science, is that it's not, at least introductory material science, is it's not so much specific analytical kind of stuff as much as it is, broad knowledge of how materials work. The subsequent classes that you would have in material science would dig into each area, each type of material, and cover them in greater depth and be much more analytical. But here we're just sort of giving you a broad overview. We got to be able to cover electrical properties at the end of the semester, optical properties. We're trying to cover so many things. So I don't go into the. I mean, there's some analytical stuff, but I think you'll all recognize, or I think you will all agree that the analytical work you've done for this class has not been terribly arduous. Right? You've not done, big, three-dimensional integrals or
we got plenty of that in the
complex, partial differential equations or anything like that. No Laplace transforms, right? There's no super computational stuff. Most of it is getting the concept and then applying that concept in the context of a question. So that doesn't mean we've covered every question in class, right? But if I ask you, where's the what was the question I asked you for give me the lattice coordinates of the octahedral interstitial sites or something like that. I asked you that question on one of the tests, right? Or not the tests, one of the homeworks, right? So we didn't specifically talk about the octahedral interstitial sites and their specific locations, but I explained where that was, and you guys have to go back to the unit cell and figure that out.
That's the 1/2, 1/2, 1/2, right?
That is an octahedral interstitial site in FCC, yes, but only in FCC.
So
in BCC, it would be the 1/2, 1/2, 0.
Yeah.
So basically, we would just kind of like draw
Or 1/2, 0.
Right. Okay. So anyway, so those are the things that are on the test. So we have definitions. There's actually another one that's kind of like a definitions kind of problem, sort of. So there's kind of two problems that are more sort of conceptually oriented. And then the other 5 are calculations of some kind.
slicing this is not an open book kind of test?
It is not an open book kind of test. And in fact, as I said earlier, I sent out the the thing from the FE review of FE manual, and I withdrew that. I mean, you guys still have it, that's fine. But because that has definitions on it, and I wanted you guys to be able to come up with your own definitions.
Should just got any definitions and took most of the equations.
Yeah, it would be too hard to go
So
through.
basically,
each time.
so
I gave you the second page, the one-page equation sheet. That's the actual equation sheet you'll have on the exam. So it has a bunch of properties for a bunch of materials, as well as a one-page thing to your email.
It was like last Thursday.
Oh,
Yeah.
They were all going crazy over there once.
So yeah, so that shows you what equations I have. So I have the dot product, the definition of the dot product, or the cosine theta extracted from the dot product, and I have the spacing between lattice planes, and I'm trying to think what else I have. Bragg diffraction equation, maybe the Arrhenius. I'm not sure if I have Arrhenius on there. Constants. I have the.
There are only like 3 actual equations.
What's that?
There are only like 3 actual
Yeah,
equations.
exactly, that's my point, and that's exactly the point I'm trying to make, there's not a whole lot of equations. I think I had the error function, I have the error function equation on there? Okay, so, and the table, and I have the table of error function values. So basically the things that are important are on there. The rest of it you guys gotta figure out on your, I mean, a lot of it's geometry, right? A lot of the knowing your way around the unit cell is geometry. What?
It's not confusing yourself.
Yes. So, does anybody have any questions? You want to go over anything on the homework? Everybody got the note about the homework being due at 8 o'clock tomorrow morning?
Yes. These books don't have that table.
Yeah, we already talked about that. I had no idea.
Also, did you fix that one problem?
Oh, no, I haven't fixed that one problem yet either. There's the one that asks for the, which are the active slip systems, and it has a whole big slew of them. There are duplicates in there. It's one of them, I gotta go in and fix the ones that are duplicated incorrectly. So, I'll do that after class here. If someone reminds me the instant I walk out the door, so that hopefully by the time, between that time and the time I get back to my office, I remember to do it.
We can take the test at whatever time we.
You may begin the test anytime between 8 and 3. And then the test has to be completed by 5. And you have 2 hours to take the test. And if you do not arrange a time with me, then do not come in at some random time and say, okay, I'm ready to take the test. I may not be there. So I have meetings from 10 to 12 and capstone from 1 to 2 tomorrow. So those will be the times I'm not available. Yes, ma'am.
We do number 3 from the homework. It's just, it's completely symbolic, I think. Yeah.
Let's see if I can.
Concentration.
Yes.
It's the Poisson method.
Oh, yeah. Okay. I still want to have it up in case somebody has another question.
We already have it.
Yeah, it's a little bit there.
Oh, you get dumb. Stupid. Hello.
Yeah, go on.
Oh wait, that's just the link. You just gotta get rid of the plugin, whatever.
Homework number 4, right?
Yep.
You just want us to email you when you want to take the test, right?
Email me when you want to take the test, yeah. Number 3, calculate Poisson's ratio for material which deforms elastically in tension with no change in volume. That is 1 plus E. Does everybody understand why that is? Correlates with the question? Why the equation that's given there correlates with the question? So in other words, we have this thing deforming elastically. So it deforms elastically, so what started out as a block that was nominally 1 by 1 by 1, and is stretched in the z direction, let's say, becomes a block that is 1 plus EZ in that dimension, 1 plus EX, and 1 plus EY. Right, that's the dimensions. Because EX and EY are going to be negative, it's going to contract as I pull one in that direction. So to say that it's the same, so basically we're taking the volume of the deformed state, 1 plus EZ, 1 plus EX, and 1 plus EY, and setting it equal to the initial volume. Okay? So what's the Poisson's ratio?
E minus EX over EV.
So nu equals minus EX over EZ for pulling in the Z direction as we are in this case. Which is also equal to minus EY over EZ. So if you substitute that in for EX and EY,
Is EX equal to EY no matter what the configuration, as long as it's pulled?
if it's a homogeneous isotropic material, yes.
Okay.
Is that a specific?
You know what I mean? You guys know what I mean by homogeneous isotropic? Okay, so homogeneous means it's the same at same properties at every point. Isotropic means it has the same properties in every direction.
So it would have to be Q.
No. No. The property, it's a material property. So in other words, isotropic, like a composite material, fiberglass, right? Wood, which is a composite material, has different properties along the grain versus across the grain. So it is not isotropic. But a chunk of copper is isotropic. It has the same properties in every direction. As long as it's not a single crystal of copper. If it's a single crystal of copper, it's not isotropic because the 110 direction and the 111 direction are going to have different properties. And if we have a polycrystalline material, randomly oriented grains, it's isotropic. Okay, so homogeneous, same properties at every point. Isotropic, same properties in every direction. So if it's homogeneous and isotropic, then if I pull it in this direction, it's going to contract in the Z and the Y and the X the same because they're the same, there's no difference. Does that make sense? So, do the substitution, put everything in terms of EZ, do out the math, and then observe what you should do based on the understanding that this is an elastic deformation.
So that's Poisson's ratio in general, or for that specific?
That's Poisson's ratio in general. Well, that's Poisson's ratio for a tensile force in the Z direction.
Okay.
It's lateral strain versus longitudinal strain. Okay, so if you just carry out the math, and then you kind of have to observe and understand what the context is when you know that these are elastic.
What exactly are we observing?
And multiply it out and find out. I don't want to tell you the answer.
So we're putting it in terms of EZ.
I would put it in terms of EZ. Why wouldn't we?
Just immediately put it in terms of EX over EZ, or can we not?
Well, I'm just saying, you only want one, so you want to get in Poisson's ratio, right?
Mm-hmm.
So you want to get Poisson's, if you plug in EX equals EZ times nu, and EY equals EZ times nu, then you'll end up with an expression, a longer expression. And I think that may be helpful. You don't have to, you can do it this way. You can just do the math this way. Multiply it out, and make the same observation. It's just, there's an observation. Write out the math, do out the math. And then, yes.
Oh, so this is kind of not related to this at all.
Okay.
This is kind of a question about the test.
Okay, let's finish, make
Oh, I
sure
thought
we're
we were
finished
done.
with this one.
Sorry.
Are you okay, because you're the one who asked?
I think so.
This is good too.
Yeah, I just gotta.
You
Yeah.
just gotta do the math.
You just gotta check through the math.
And then there's some assumptions you can make once you see the thing right now.
Okay, won't there be EZ cubed terms in it?
There will be.
How are we supposed to use that? Like,
I don't know,
just
what
gotta
do you think you do with that? What do you do with that?
solve,
What is EZ?
it's a strain in the.
No, the correct answer is addition and subtraction. What's easy? Anyway, sorry. What is EZ?
Strain in the Z direction.
Strain in the Z direction, right. If it's elastic strain, give me an approximate numerical value for EZ.
Whatever you want it to be.
Nope, can't be whatever you want it to be.
Less than 1.
Well, it's gotta be less than, it's gonna be well less than 1
Yeah.
if it's elastic strain.
Uh,
Right, elastic strain is a very small number.
yeah.
When I drew remember I drew the stress strain curves and I said I drew them kind of like this?
Yeah.
And I said that's terribly exaggerated. In
Right.
reality, they look like this.
Right. But
Right.
how does that help us with the ratio?
So the elastic strain here is a very small number.
Okay. So
So
then
that's all I can do to help you.
so we get a number for easy, like an actual physical number.
No, you don't get to just look at it knowing that EZ is a kind of a smallish number.
Oh.
Okay, now let's move on. What do you got?
So, how did you feel? So you
I feel good. Ooh, I feel so good.
so you have, let us know that there's 2 conceptual and like 4 equations.
2 plus 4 equals 6, and I said there were 7 problems. But
And
yes.
then 1 vocabulary.
So I said actually there are 2 that are more vocabulary conceptual, and then 5 that are.
Oh, it's 4. Sorry.
5 and 2.
5 and 2.
Right.
Would you be, so then one of those conceptual is gonna be vocab.
Well, yeah, right. They're
And
both
then-
vocabulary essentially, but you've got to. I'm just coming at it from different perspectives.
Would you be completely against telling us the topics of each of those different questions? So like.
There you go.
The 5, yeah.
I'm just doing a lot of stuff, bond types.
Still lost cause, I guess.
Yeah, it's awesome.
Yeah.
They are not intended to be obscure definitions. The vocabulary I'm after is more sort of mainstream
We talked about it more than once.
material science vocabulary.
Hipstery, you know,
What's that?
mainstream,
Hipster.
hipstery.
Yeah, no.
If we were to like review the homeworks and like be able to feel confident about the homeworks that we've done, would you say we should feel good about the test?
That's a good step toward doing the problems. The homeworks don't have definitions on them.
Yeah,
Right.
other than like definition wise.
Right, so other than the vocab stuff, I did not take the test problems from the homework problems,
Mhm.
but they are similarly designed. Okay, so, I don't want anybody coming back and saying, wait, you never asked that question on the homework. No, but it's, okay.
So it's like we have to memorize all these stress, strain equations that we've been using for this.
So yeah, the basic ones you need to understand, because those are kind of definitional, like Poisson's ratio, right? That's a pretty simple definitional equation. So those you are expected to know on your own. If it's not on the equation sheet that I think you have there, okay. So if it's not on that equation sheet, then you need to know it. But everything that's not on the equation sheet really is kind of a basic ratio. I mean, that's all these things are. Stress, strain, true stress, true strain, all basic ratios. Nothing too complex in those equations. So yes, you need to do
Back
those.
to napkin stuff.
What's that?
Back to the napkin stuff.
Back in the napkin stuff, exactly.
It's Arrhenius on here, which I don't think is like a pretty sheet.
Like it's it take time.
So with Arrhenius, yeah, it's not on the equation sheet, right? Isn't diffusivity on there? I thought diffusivity was on there. Yeah, diffusivity is on there.
Yeah, that's different.
That's an Arrhenius behavior. So in other words, if I gave you a diffusivity, which is a Arrhenius behavior, you've got to be able to find the activation energy given a rate, or find a rate given the activation energy. Okay. So that's just one example of an Arrhenius behavior. We'll have others throughout the semester. Yes?
I just have some questions on the stress strain plots. It's not useful to think of stress as a function of strain, is it?
Not really, no. Because, I mean, you can, yes, up to a point, right? Up to that point you can, because it's a linear relationship, right? For this section, we know that stress is equal to the Young's modulus times strain. Actually, I shouldn't draw it that way, because this is the engineering stress diagram. So stress is equal to E times E. Okay, but, so there is a functional relationship. Stress is a function of strain, but only up to the yield point. After that, we don't really have a functional definition.
Big U, the modulus of elasticity.
Right, or Young's modulus.
But what it does tell you is that, because there's no way to reverse the process once you start getting to that hump. Say,
Right, once you get past this, anytime you get past this, right, it extrapolates back down. So you're left with this plastic piece, and then if I drew a straight line down, an elastic piece. So there's an elastic and a plastic deformation. Right? Where the slope of this left dotted dashed line here is E, the Young's modulus.
so what this tells you, because it's the strain is a distance idea.
Strain is a percentage
It's a percentage of
of
distance.
percentage of length, yeah, percentage of distance.
So that always keeps increasing, but the amount of load, which is pressure, right, the
Right, stress.
stress, decreases for each.
Why is it okay, somebody tell me, why does it decrease over there?
Those the materials thinning.
Right, necking, right? It's thinning faster than it's strengthening. And so the stress goes down. Because in engineering stress like this, it's divided by the initial cross-sectional area. So we don't take into account the fact that it's increasing. That's why this parent stress drops off. In reality, the true stress continues to increase until it breaks. Because the true stress is divided by the instantaneous cross-sectional area, so as it necks, the stress goes up. If I had to emphasize one piece over another, I would emphasize, and this is not for you to study everything. But I'm probably more inclined to ask mechanically oriented questions over, you know, something else.
Thermodynamics.
You know, I mean, it's just, I probably shouldn't even say that. I'm gonna make you feel like, oh, I'm just gonna study the mechanical stuff and you're gonna miss the problems on whatever other topics there are. Yes?
Speaking of that kind of stuff, not the mechanical, but the other stuff, can you kind of do a brief overview of the directions and planes? Because that seems to be something that I can't visualize very well, so
Okay.
I pseudo understand the concept.
So we have directions and planes.
I'm trying to get the whistle.
What do those correspond to? Can anybody tell me which one's which? Yes, ma'am.
I think so. Direction. The brackets are direction,
The square brackets?
yes.
So this is the direction.
The triangles, ones are plane. And then parentheses are family of directions. And the curly's a family of planes.
Anybody agree with her? Uh-oh.
What did I do wrong?
What do you disagree with?
You have to flip the family of directions. Actually, I think I'll read the last.
So you're saying this is a plane,
Yeah.
and this is a family
Of directions.
of directions, and that's a family of planes?
Oh, it says it right there, yeah.
Oh, yeah, it does. Yeah. Funny the way that works. Okay, so that's correct.
That's right.
And there,
Isn't the blank one to the left just the position?
Yeah, this one over here? Yes, that's the position, yeah. Very good. All right, so first of all, that's one important thing, right? So I asked you for the Schmidt factor, like the problem, one of the problems asked for a Schmidt factor or something.
You asked for a Schmidt factor?
Isn't one of the homework problems asked for a Schmidt factor?
Yeah.
Oh, it requires you to calculate,
Let's
it
go
doesn't
with test,
specifically
yeah.
say Schmidt factor. Okay, tells you to calculate, basically you have to calculate Schmidt factor. You gotta know which is the direction and which is the plane, right? Because how you handle these things, right, you need to know, if I asked you what directions are in this, the whatever plane, right, you've gotta know, or if I gave you this and said, here, what's the slip system, you gotta know which one's the direction, which one's the plane.
well, why? Because they're both cosines.
No, yeah, but you can't define, in other words, if I say, what are the slip system, the close pack slip systems for that in BCC? No, not in FCC, sorry, in FCC. So I said, give me the close pack directions for that in FCC. Well, I have to know that that's the 111 plane, so that I'm then providing the 3 directions that go with that. Right? Alternatively, if I told you, what are the slip systems associated with that, right, you'd have to know that there are 2 directions, that are 2 planes that are associated with that particular direction.
Really?
Yeah, the 110 is the diagonal at the bottom of the cube. So, right, that's this direction right here. And there's this plane and this plane that both involve that direction.
So
For FCC, yeah, right, for FCC. So the point is, you still got to be able to identify what's a direction, what's a plane.
Right, but in terms of actually calculating the Schmidt factor.
Schmidt factor is the same.
You still just do the dot product of.
It's a dot product of the dot product of the tensor direction with the plane direction, and the tensor direction with the plane orientation, the plane itself, which is the direction normal to that plane. So it's still the dot products are done the same, yes. Okay, now, who asked the question about the directions? Okay, what is it in particular?
Okay, this may seem very elementary that we're going back to that, but say we got a cube like that. How am I to know that your 110 is that point right there?
Okay, so the key in finding all these things is to pick a corner and work from there. So if I have,
So if you were gonna have a problem where you were talking about a specific point, you would also tell us a corner with
Nope.
base ourselves on?
no, you pick your own corner. I'm not actually going to draw the thing. I shouldn't draw the atoms.
Pick a
Okay.
corner.
So let's say you pick the back corner as your reference point.
Okay.
Okay. So if I ask you for the 111 direction or the 101, well, let's do the 101. So first of all, I have to define what's x, y, and z, what's a, b, and c. Right? So I might define, that's my center, that's my origin, I'm going to call that a, b, and c. Follow that?
Okay.
So the 3 dashed lines are a, b, and c. The 101 direction, I come out 1 in the a, 0 in the b, 1 in the c. It's that direction. And the best way to identify that on a plot or on a drawing of the cube is to put little dots at the 2 places where it intersects the cube. So I can tell, because otherwise you draw a line, it could be, three-dimensional, it's a three-dimensional representation. I need to know where it's entering and exiting the cube. Okay? Does that make sense?
Yeah, that makes sense.
So that's the direction.
So find the direction. So when you're finding a direction, you start from a point on the line. Right? My origin is on the line that I want to draw. When I'm trying to define a plane, I pick a point that is not on the plane in order to define the plane.
So
So to define a line, the point you start with is on the line. To define a plane, the point you start with is not on the plane.
Do we need to say what spot we're using as our origin, or can we just move to figure that out?
You could get anything, any information you give me that you think would be helpful, probably be a good thing to include.
Can you go over finding the plane then?
Okay, so let's go over finding a plane then. So now let's find the 101 plane. Okay, we found the 101 direction, let's find the 101 plane. So to find a plane, what's the key with a plane?
Not on the point.
So I start with a point that's not on the plane, right? And then what do the 101 tell me?
It's perpendicular.
Where it intersects the axis.
Right, talk about where it intersects the axis, right? So to find the 101 plane, I want something that intersects A at 1, B at 0, and C at 1. So I go up, so it intersects C at 1, intersects A at 1, and it never intersects B. So it is this plane that I would draw. Which, by the way, is perpendicular
Did you say that was
to the 101 direction. That was the 101 plane. So the 101 plane and the 101 direction are perpendicular to each other in a cubic system. Yes.
So earlier you had that like kind of sloped triangle that was from like the 0, 0 point to
The 111 plane of the
Yeah.
SCC. Yeah.
Yeah, I'm confused on where, because like that, to me it appeared when you drew that it would be crossing, oh no, I have to choose a spot that's not on.
Right. So now, if I wanted to do the 111 plane in this drawing, across the A at 1, across the B at 1, across the C at 1, it's then a plane connecting those three. That's the 111 plane.
That's what
Does that
has
help?
me off.
And then the other direction, doing it the other direction, we actually had a process. We, you know, where we, if it starts out, if you draw the plane first, and then you need to find the coordinates of that plane, or the indices of that plane, then I find the intercepts, right? So the intercepts here are 1 for the red one. Well, hang on, let me draw another one. Let me do a different plane. Let's draw this plane. Okay? Everybody see the plane I'm talking about there? So now pick a point not on the plane, I'll pick the back corner. Find the intercepts. It intercepts A at 1, it intercepts B at 1, and it intersects C at infinity. Right? Those are the intercepts. I invert those. 1 over 1 is 1, 1 over 1 is 1, 1 over infinity is 0. Clear the fractions. There are no fractions. That's the 110 plane.
Where'd you get the infinity?
It never
Because
actually-
that plane goes infinitely in the C, it never crosses the C axis.
Yeah, so how did you get it?
So the intercept of the A axis is at 1. I'm starting with this point, not on the plane. The intercept of the A axis is at 1. The intercept of the B axis is at 1. And the intercept of the C axis is at infinity. It never crosses the C axis. Then I invert those. 1 over 1 is 1, 1 over 1 is 1, 1 over infinity is 0. And there's no fractions to clear, so it is the 110 plane.
So it's always going to either cross at 1 or not cross it in a plane.
No, I mean, I could do this plane. I gotta get another color. I could do this plane. You see that plane? All right, so that one crosses the A axis at 1. It crosses the B axis at infinity. Keep doing that. And it crosses the C axis at 1/2. Inverting, 1 over 1 is 1, 1 over infinity is 0, 1 over half is 2. Clear fractions, I don't have to, that's the 102 plane. Does that make sense? And then if I wanted to go back and find the 102 direction, right, I would pick the same point. The 102 direction would go 1 in the A, 0 in the B, and 2 in the C. See that I'm going into the unit cell above it? So now that line goes here and crosses the unit cell, there.
It is perpendicular to that.
And it is in fact perpendicular to the green plane. So it crosses at 1/2 here, yeah.
Can we now take this discussion into the hexagonal?
Hexagonal?
Hexagonal.
Hexagonal.
Just not include a hexagonal close pack problem on the test.
All right, let's just not do that.
Sweet.
So you say there's not gonna be one on the test then?
Are you serious?
You didn't say that, Daniel.
Yeah, you never say that on camera,
Okay.
Daniel.
Anyway, okay.
Okay, so then if you took the dot product of the direction and plane as perpendicular to it, you should get 0, right?
Right.
So 102 dot 102.
No, so I can't dot the line with itself, right? Because the 102 direction,
You have to choose a direction.
you have to choose a direction in the plane to get, you see what I'm saying? The 102 direction is by definition perpendicular to the plane, so I'd have to take the dot product of that direction with a direction that's in the plane.
Oh.
Right, so here, the 0, 1, 0 direction, right, coming out along the b-axis is in that plane. So if I dotted 1, 0, 2 with, if I dotted 1, 0, 2 with 0, 1, 0, indeed, I would get 0. Right? But also, I could also look at this, that direction's in the plane, right? Which is that direction is the 2 bar 0, 1 direction. Right?
Or 101, or 1 bar 0.
This direction here is the 2 bar 0, 1 direction. So going 2 in the x, 1 in the y, or 1 in the z, and 0 in the y. So if I dot that with 1, 0, 2, I'll again get 0. Negative 2 times 1 and 1 times 2 add to 0.
Not to,
Which is the one? 0, 1.
it's just kind of an ugly 2.
Sorry.
Wait, which is the 0, 1, 0 direction? Isn't that, it's not in the plane.
The 0, 1, 0 direction, this right here is the 0, 1, 0 direction.
It is? But why is it
Because you're this way, one
C
way.
and the 1 down?
I have to pick, remember, to do a direction, I have to pick a point on the line.
Right.
So I pick this point, and I go 1 in the B, and
That's
0 in the
right.
A and the C, so
Yeah.
it's 0, 1, 0.
That's what it was.
Is that, you were asking about the planes and directions, right? Okay, you're good?
And better.
And so like families of planes and families of directions are kind of, if you would like rotate it or something, it still looks the exact same.
Right. So generally speaking, if I have, for instance, the 101 family of planes, that's going to include 101, 101 bar, 110, 11 bar 0, 011, 011 bar,
So you have to like pop them all.
and the minuses of negatives of all of those.
Can we talk about the types of defects? Yeah.
So, but Britton had his hand up, so we'll let him answer, ask the question. Go ahead.
Do you have those memorized? Were you doing that graphically in your head, or is there something analytically with the numbers that you can figure that out?
So A, B, and C are basically equal. So depending on how I rotate the crystal, my 0 could be in the B, C, or A direction. And then I have 1 in each direction or 1 bar. Okay? Either going, you know, so the family, in other words, or I don't know if it's planes or directions or planes. So the 101 plane, didn't I draw the 101 plane already? Yeah. The black one in there,
Oh, wait.
right? That's the 101 plane. If I pick the 101 bar plane, it'd be 101 bar, so it would cross, it's essentially this one. That's the 101 bar plane. So I start here, start up here, I go 1 in the X and 1 bar in the C. Those two are the two that cross each other like that. And then, as I said, you have 1, 2, 3, there are 6 of those, right? And they're defined by the direction, in this case, B, here, where they cross.
But 1 bar 0, 1 would not be part of that family?
1 bar 0, 1 is just the same plane looked at from the other side. 1 bar 0, 1 and 1, 0, 1 bar are the same plane viewed from 2 different sides. Just like 1 bar, 1, 0, 1 bar and 1 bar 0, 1 are the same direction going either direction, right? I don't think they're sliding that way or this way, but they're the opposite pointing vectors in the same direction, same line. Right, because these 1 bar 0, 1 and 1, 0, 1 bar are defined, since the planes are defined by the normals, that's the normal going this way or the normal going that way, it's the same plane. Is that, okay. Now what you ask about, what were you asking about, Sonny?
Just the defect types.
Defect types, okay, so we have vacancies, interstitials, substitutional, impure, it's all the point defects, all the 0-dimensional defects. So we can put extra stuff in or take stuff out of the lattice. Right, so
Is that mostly just, that's qualitative stuff for the most part, right?
yeah, we did talk about the vacancy formation following Arrhenius behavior. So there's some measure of that.
What about the whole, what is that vector called?
Burger's vector?
Yeah.
Okay, we'll come back to that because I'm going to do the point 0 defect, 0-dimensional defects first. It's 5 minutes. All right, so we have vacancy, right? That's a vacancy,
Yep.
right? We have substitutional impurity. I think that's what I have. That's one of the ones up there, right? Substitutional impurity, where I have an impurity atom occupying the lattice site. I have an interstitial impurity, where I have the impurity atom sitting between the lattice sites. What else do I have? Self-interstitial. I have another of the same atom stuck in interstitially.
Is there feel like a dual atom system and like they shift down? No?
There's the alumina magnesium problem that we did in homework, where,
That's pretty
right, so there's a Frenkel and a Schottky defect.
Track, yes, right.
Right. Yeah. Right, those are what you're talking about?
Yeah, I think track is one.
So, anyway, so it's a paired, a Schottky defect is a paired, a Frenkel defect or a Schottky defect is a paired defect. So you have a vacancy that moves over to somebody, an atom moves someplace else, and it's the pair of those two that form the defect. One-dimensional dislocations. If I then so here, we have an edge dislocation. Located there. Everybody see the edge dislocation? And we find the Burger's vector of any dislocation. So Burger's vector is associated with a one-dimensional defect, a line defect. In this case, the one dimension goes into the board. Right, the edge of this dislocation line is running into the board, so it's a one-dimensional defect. And we find it by picking some atom nearby and counting the loop around it. Actually, let's pick an atom down here. Go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. The difference between where we started and where we ended is the Burger's vector.
So it doesn't depend on where it is?
Where what is?
Like, we could start it anywhere.
Right, and the Burger's vector would always be one atomic spacing, one horizontal atomic spacing in this case.
What about its direction?
generally speaking, the dislocation doesn't have directions unless it's
What's it
moving.
called, inverted spectrum?
So, because if I started, generally the Burgers vector is defined in terms of like a clockwise rotation or something. So if I start here, I go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, I would end up with that difference. But I don't know that it's really, because it depends on which direction you go, clockwise or counterclockwise, you get opposite senses. So there's edge dislocation here, and then a screw dislocation, which is more complicated to draw. Remember, I had to use the overhead projector for that because it was a little more complicated. And then the mixed dislocation is actually the line that connects the edge and the screw. And then twins, we talked about twins, grain boundaries and surfaces. There was pretty much qualitative. Right, so if I asked you to give me a list of two-dimensional defects, you'd have that list. Is that enough on defects? Anything else? In 1 minute or 30 seconds, whichever it is.
What's MOR?
Modulus of rupture. That was a different expression. Right, for another way, that was a way of finding out about the strength of ceramic bars, for instance, where you can't put them in a tensile machine. And so we measure a modulus of rupture. It's kind of the equivalent of a tensile strength, but it scales in the way that it's a 3-point bend.
Did you give us that equation or no?
I did not keep you that equation.
So that's all we should memorize.
What was
Or should it? That's what I was getting
what was the one where you had that point and you like stabbed it?
Indentation,
Yeah.
hardness indentation, yeah, indentation.
Yeah, that was supposed to be qualitative too, right?
Yeah, there is an actual equation for that, for calculating the Grinnell hardness number, but most of the time you don't actually use that. It's already built into the system that measures the hardness. So you just have to understand what hardness means more than you have to worry about quantifying. All right? Well, hopefully that's helpful for everyone. But please don't forget to email me what time you will be beginning your exam, so I know when to go. Yes, it's a paired point defect. There are two of them, but they're still a pair of points.
Alright.